Hi, everybody. So today what I'd like to do is take you through an example problem where we're finding the potential of a spherical shell of charge, and then we're using that potential to find the electric field of that spherical shell of charge. So this is from problem 2.7 in Purcell and Morin. So let's go over what this problem asks us to do. So we have a spherical shell of charge, and it's got a radius big R, and it's got a total charge, big Q, uniformly distributed over the surface. So we're going to find the electric potential or the voltage, which in Purcell and Morin chapter 2 is called phi. And it's going to be at some distance A from the center of our shell. And then we're going to find the electric field by using the expression that the electric field is minus the gradient of the potential. Okay? So I've got a little sketch drawn of what the problem looks like here. So here's our spherical shell of charge, and the problem suggests that the best way to approach this is to slice the shell into little rings, right? And the little rings would have some little differential area unit, and then you integrate over the area of all of those rings over the entire surface. So that's the strategy. And it also suggests that you need to use the law of cosines to get this done, okay? All right, so let's get into the equation here. So remember that the potential, what we're going to do is we're going to use the expression for the potential, which is the integral of k dq over r here, all right? Now r in this expression is the distance from the charge to the point in question, or the observation point, okay? So that's there. And then the, oops, let me label this correctly. This is going to be R, okay? And so here, dq is the differential element of charge, okay? dq. And then you integrate over dq. But remember that in order to integrate over dq, you need to translate that using the charge density appropriate to the problem. Okay, well, this is a surface charge density because it's a spherical shell and the charge Q is uniformly distributed over the surface. So that means that we're going to use sigma for our surface charge density. And here, the surface charge density is uniform. So it's going to be the total charge, big Q, divided by the total area of our spherical shell, which is 4 pi big R squared. So that's our surface charge density, right? And then our dq would be equal to sigma times dA. Okay, well, the way that they suggested that we do it is we have these rings and we integrate over the rings. And so that would mean that our little differential area unit would be the area of one of these little rings, okay? All right, so let's go to the next page here and visualize this. So here I've got my ring, right? There's my ring. Okay. And I'm going to fill my ring in here so it's obvious what I'm doing. So here's the radius of my spherical shell. Here's my point in question, right? This is A, the distance from the center to the point. And then we'll call this right here R. Okay, so first things first, dA. Well, dA here would be the area of one ring, right? Now, if you unroll the ring, it's going to make a little rectangle, right? Okay, so if I call this angle from the z-axis as labeled here theta, right, which is a conventional choice for spherical coordinates, then that means that the thickness of our little rectangle would be equal to r times d theta, because that would be, for example, here, this is ds, right? The little arc of our circle. And we've already gone over how the ds, a little arc length segment, would be r times d theta. So this thickness here is big R d theta, where r is the radius of our spherical shell. Okay, now we can find the circumference, right, of this ring. And the circumference of the ring is going to be the length of our little rectangle. Now, this value of the circumference is going to change as we change our value of theta. We're going to integrate here over theta. And so the value of the circumference is going to change depending on how big the ring is, and how big the ring is depends on theta. So how are we going to find this value? Well, let's call the radius of our ring at an angle theta, we'll call that r prime, okay? And the circumference of the ring would be 2 pi r prime, okay? Now, let's put that in terms of the variable that we're going to integrate over. Let's put it in terms of theta and some constants. So you can see here that I have a right triangle, right? And it looks like that, right? And so I can write r prime in terms of big R and theta by using sine of theta is equal to r prime over big R. And therefore, if I plug in here for r prime would be big R sine of theta. And so the circumference of my ring would be 2 pi big R sine of theta. Okay, so now we can write dA, which would be the area of one ring. The thickness of that little ring would be r d theta, and the circumference of the ring is 2 pi big R sine of theta. So that means that dA is going to be equal to 2 pi r sine of theta times big R d theta. And then that gives me 2 pi r squared sine theta d theta. So that's my dA. And then my dq would be equal to sigma dA, which would be equal to sigma times 2 pi r squared sine theta d theta. So that's what we're going to plug in for our dq in our integral. Okay, now the next thing that we have to figure out, because phi is equal to the integral of k dq over r, we have to figure out what little r is here, okay? So in this case, this is where the law of cosines comes in, okay? Because as we change our value of theta, of course, the value of little r is going to change, right? When theta is 0, then little r is going to be a minimum, and when theta is pi, then it'll be maximized. And so how do we write that? Okay, well, this is where the law of cosines comes in. So if you need a reminder, the law of cosines is like this. You don't have to have a right triangle to use the law of cosines. It's not like Pythagorean theorem that way. All you have to have is a triangle. 3 sides, we'll call them little a, little b, and little c. And the angles opposite from those sides we'll call the capital letter. So the angle opposite from side C, I'll call capital C. The angle opposite from side A, I'll call big A. And the angle opposite from side B, I'll call big B, okay? Now the law of cosine states that I can say that c squared, I can just pick a side, right? And that c squared is equal to a squared plus b squared minus 2ab cosine of c. Okay, so that's the law of cosines. And so this leaves it generic, okay? Now, how would this apply to our problem? Okay, well, we want side little r, okay? And we're going to integrate over theta, and theta is the angle opposite to side little r, okay? And so what I can say here is that little r squared is going to be equal to the sum of the other two sides, which are called here a squared and r squared, big R squared, right? And then it's going to be minus 2ar cosine theta, okay? So now we've got the law of cosines, but applied here to our value of r, okay? So if we take the square root of this little r squared, then we can plug that in, and now you see I've got little r in terms of some constants and my integration variable, which is theta. So let's plug that in, okay? So I've got c is equal to the integral of k dq over r. That's going to be equal to the integral of k, and then dq would be sigma times 2 pi r squared sine of theta d theta, as we found before. And then I'm going to plug in little r here, right? And little r, as we saw here, was the square root of a squared plus big R squared minus 2AR cosine theta. Okay. So in physics speak, we have reduced this to quadratures, as they say, right? We've got it in terms of an integral. And now we just need to solve for that integral, okay? Now, we're integrating over theta here. So one more step is we need to plug in what our limits of integration are. And remember that here we have our bit. We're integrating over our angle theta, and theta runs from 0 to pi. Okay, so theta runs from 0 to pi. Okay, so let's evaluate this integral. So in this case, we can pull the constant out front. Everything that's a constant, let's go ahead and pull it out front so that it's not so confusing. So k is a constant, and sigma 2 pi r squared, those are all constants. So that can come out front to make things a little more straightforward. And now inside, we're just integrating over sine of theta d theta over the square root of a squared plus r squared minus 2ar cosine theta. Sorry if my handwriting stinks. Okay, there you go. Now, in order to solve this, let's do a substitution. So what are we going to subs? Well, I'm going to call the stuff within the square root there, I'm going to call out y. So y is equal to a squared plus r squared minus 2ar cosine of theta. And that means that dy, dy is going to be the differential of that. Now, a, big R, those are constants. And so when I take the derivative of that, it just goes to 0. And we just end up with minus 2a big R times the derivative of cosine of theta, which is minus sine of theta d theta. Right? So that means that dy is 2ar sine of theta d theta. There we go. Okay, so now you can see why I made the brilliant choice that I did to plug it in. We've already got a sine of theta d theta here on top. And so that means that we can solve for what we've already got. So here we have sine of theta d theta is equal to dy over 2a big R. So now I can plug that in, and I end up with phi is equal to, okay, times 2 pi r squared, and then over 2ar out front, right? That pulls out front. And then what I have here is the integral of dy over y to the 1/2. Okay. Okay, so this integral I can do. Now, for those of you new to my style of integration, when I do a substitution, I just do the substitution and then I find the integral, right? I find the value of the integral. Then I plug my original thing back in, and then I use my original limits of integration. And that way I don't have to switch the limits of integration up here, which can be kind of confusing. Okay, so that's the way I like to handle it. So when I have my substitution, I leave it as an indefinite integral. Okay, so the integral of dy over y, that's the integral of y to the minus 1/2 dy. So you increase the power by 1 when you do an integration. And so that means that what I've got here, I've got k times 2 pi, whoops, I dropped my sigma somewhere there. There we go. Okay, times 2 pi r squared sigma over 2ar, right? I'll simplify here in a minute. And then I end up with 2y to the 1/2. And then I'd have to evaluate that. But before I do that, I'm going to subs back in my original value of y. So moving on, my original value of y was a squared plus r squared minus 2a for r cosine theta. So if I plug in for that, then I get k times, here we go, 2 pi r squared sigma, right? Yep, 2 pi r squared sigma over 2ar. Right? And then I have the 2y to the 1/2. And then that's going to be a squared plus r squared minus 2ar cosine of theta to the 1/2 power. And then I'm going to evaluate that from 0 to pi. Okay? All right, so when I plug in for this, the cosine of pi is going to be -1. And so that means that I end up with this value, okay, here, 2 pi r squared sigma over 2ar, and then I have a 2, okay? And then I have here the square root of a squared plus r squared plus 2ar, right? And then for the second one, cosine of 0 is 1. And so that means that in the second one, I have a squared plus r squared minus 2ar bit there. Okay, now if you look at this term within this square root sign, then that's just a plus r squared, right? And then within the second square root sign, that's a minus r squared, okay? So if I'm going to do the square root of that, then I would end up with, respectively, a plus r, and then for the second one, the absolute value of a minus r, okay? So I'm going to at least cancel this 2 here, like that. Oops. And what I end up with then is a plus r minus the absolute value of a minus r. And that's my potential. Now, the value of what this is depends a little bit on exactly where the observation point is. So where is A? Okay. So if A is outside of the spherical shell, A is greater than R, then you have one set of conditions. And if A is inside the spherical shell, A is less than R, and you have another set of conditions. Okay. All right. So if A is greater than R, then the absolute value of A minus R would be equal to just A minus R, and you could write it that way, okay? However, if A is less than R, then the absolute value of A minus R would be equal to R minus A, and you would write it that way, okay? So that's what we've got there. Okay, so let's concentrate first on the A greater than R case. So here, first, we have A greater than R. Okay? So if A is greater than R, and for all totally, let's now go ahead and start simplifying here. Okay? So here we have K times 2 pi big R squared sigma over AR. Right? So that's what we've got there. And then we have A plus R minus A minus R. Okay, so simplification time. So here we've got an R outside, R squared outside, and then it's got an R on the bottom. So we're going to cancel one of those out. So we have 2 pi K sigma R over A, like so. Okay. And then within, we would have A plus R minus A minus R. The A's would cancel out, and that would leave 2R on the inside. Okay. Okay. So this gives us 2 pi K sigma R squared. Sorry, 4 pi K sigma R squared over A. Okay, now sigma times 4 pi R squared is equal to big Q by definition, right? So that means that our potential, phi, oops, is going to be equal to K times Q over A. Okay, well, if you've been paying attention at all in potential, then this is the potential for a point charge. Yay. Way to go, okay? And I bet you're thinking to yourself, we went through all that to derive the potential for a point charge. Yes, yes, we did. But at least now you know that it's right? Okay. Okay. No, I'm just teasing. And so now let's consider the a less than R case, all right? Okay, now this is the slightly more interesting case, right? So if that's the case, then what we've got, going back to our expression here, we would have K times 2 pi R squared sigma over AR, and then times A plus R minus, right? And then R minus A. So it would be B is equal to 2 pi K sigma, right? R squared over AR. And then times A plus R minus R minus A. Okay. So it looks very similar to our previous case. We're just switching the order again of that second term. Okay. So what we have here is then 2 pi K sigma R over A. I'm going to go ahead and simplify. And then here you have A plus R minus R minus A. And so the R's cancel out here. And then on the inside, you have 2A, right? So this is going to be equal to, the A's cancel out, and you end up with 4 pi K sigma. And then your A's cancel out R, okay? All right, now, what does this mean? Well, first of all, if you look at this, this is all constants here, okay? All constants that do not depend on A, okay? So what that means is no matter where you put your point inside of your sphere, it doesn't matter because the potential is always going to be 4 pi K sigma R, right? It's going to be the same throughout the sphere, okay? So let's plug in here. Remember that sigma is equal to Q over 4 pi R squared. So if we plug that in, then phi is going to be 4 pi KR times sigma, which is Q over 4 pi R squared. Okay, the 4 pi's cancel out, and then you just end up with a potential of KQ over big R. So what does this tell us? This tells us that the potential inside the sphere is going to be equal to the potential at the surface of the sphere, which is the potential for a point charge at that point, okay? So this is a constant, as we discussed, all right? And it does not depend upon the position of A. Okay, so now let's find E. E is equal to minus the gradient of the potential, all right? So now this is going to be the gradient of the potential with respect to the radial coordinate, okay? So here, what that would be is E, magnitude of E, would be equal to minus D, and the distance there, the thing that would vary now is A, dA, dA of the potential. And that's because we're only picking up the radial coordinate because there is no dependence in there on any of the angular quantities. So there's no change in the potential as you vary theta or phi. And that makes sense because there's a symmetry there. You could always rotate your coordinate axis and then just put the distance from the center of the sphere no matter what, right? Okay, so now for A less than R, right, then the magnitude of E would be equal to minus DDA of KQ over big R, which is equal to 0. So the electric field inside the sphere is 0. Now we could have told you that from Gauss's law, right? We could have told you that from Gauss's law. All right, now, once you get outside, the magnitude of the electric field is minus DDA of KQ over A. Okay? And so that's going to be KQ over A squared. And as you know, that's the electric field due to a point charge when you're, outside of the point charge. Okay, so this exercise shows you how to deal with charge distributions in spherical coordinates. And you know that you can trust the way that we set this up because we end up with results that we're already familiar with from dealing with them from Gauss's law and also just by dealing with point charges. And of course, once you get outside of a sphere, well, it starts to look like a point charge, doesn't it? Okay. I hope that was helpful, and I'll see you in class.